Hi guys, and welcome to today's video. In today's video, we will see how the MPU or memory protection unit is used to create a custom memory region in terms of read, write and execute protection, and how the MPU is playing a big role within the ARM Cortex-M microprocessor families. MPU or memory protection unit is a hardware block part of the ARM Cortex-M microprocessor. This hardware block is an optional one, means we can have an ARM Cortex-M microprocessor with the support of MPU, and we can have other ARM Cortex-M microprocessor without the support of MPU. Cortex-M3, M4, M7, M33, M35 and so on can support the MPU. However, Cortex-M0, M0 Plus and M1 in general doesn't have the support of MPU. Nevertheless, the M0 Plus microprocessor may have the MPU integrated within it. The MPU is a region-based model, means we can define multiple memory regions which has each one a start address and limit address, and then we assign certain access privilege to this defined MPU memory region, whether in terms of read, write or execute. The MPU by itself is part of the ARM Cortex-M processor block and is located between the Cortex-M core itself and the rest of our system-on-chip system. Hence, any read, write or execute transaction first will go through the MPU, and if there is a match between the address to access and one of the MPU memory regions, then the corresponding attribute will be returned to the core. It means if this read or write or execute transaction is allowed to that memory region or not. If not allowed, then the core will trigger a memory managed fault. If allowed, then the transaction will go all the way down to the rest of the system. MPU-based region can be configured dynamically at runtime, means we can redefine the start address and the size of each MPU region, as well as we can assign different privileged access rights to each of those MPU regions. If we combine those MPU region dynamic configuration with an RTOS based system, we can have for each RTOS based task different view for those memory regions. For instance, for task number 1, we can disable the access to the IO peripheral registers number 0. However, we can enable the access to the data segment assigned to our task number 1. And this is of course thanks to the MPU region configurations. For task number 2, we can enable the access to the IO peripheral number 1 registers. However, we can disable, for instance, the access to the other IO peripheral registers, whether it is peripheral 0 or 2. And we can enable, of course, the access to the data segment assigned to our task number 2. Same thing for task number 3. We can dynamically reconfigure the MPU regions to disable, for instance, the access to the IO peripheral number 2 registers. However, we can enable the access to the data segment assigned for our task number 3. In terms of programming model, the MPU has a set of registers that allow defining the boundaries of our MPU regions in terms of start address and the size, as well as defining the different access rights assigned to our MPU regions. The type register will give us an idea if the MPU is supported by our ARM Cortex-M microprocessor or not. Also, it does give an idea of how many MPU regions are supported by our MPU block. The control register will allow globally enabling the MPU hardware block. The RNA register is used as input to our MPU mux, means it allows selection of which MPU region we want to configure. R bar and RASR registers are the one used to define the different access rights as well as the boundary of our MPU region separately. So we need to select the MPU region to be defined here through this RNR, and then the MPU max will select the corresponding R bar and RASR register associated with this MPU region. If we want another MPU region, for instance number 1 or 2, then we put the number here, and then the corresponding register associated with this region number 1 or 2 will be selected. The R bar used to define the base address of our MPU region. The RASR register is used, for instance, to define the size of our MPU region to protect, as well as assigning the different access rights to our MPU region, whether in terms of read, write, or execute, as well as the memory attribution in terms of cacheability or bufferability. And here is an example, as you can see. So here we define our MPU region number. We put it as part of the RNR register. Then the corresponding R bar and RASR will be selected. This is of course abstracted to the user. Then we define the start address of the MPU region to be protected via this R bar register, and then we define the different access rights as well as the size of this MPU region to be protected via this RASR register. And we continue all the way to the different MPU regions supported here. As you can see here, guys, this is our RNR register. This is used actually to select the number of the MPU region to be configured. And based on this number, the MPU will act as a max and will select the corresponding R bar and RASR register to be used. How many MPU region supported here? This depends actually from the configuration of our system, but you can get an idea via the MPU type register, which reflect how many MPU regions are supported. However, the number range in general between 8 to 16. This is the R bar register, and as you can see, this is used to define the start address of our MPU region. Here we cannot define the full 32 bits of our register. Hence, the start address must be assigned to this limit. Of course, you will need to see the configuration of your system to know this number n, and hence know the alignment of your MPU start address. Valid bit will be used to determine if the configuration is active or not, or valid or not. Means we can redefine the region number to be used instead of using the RNR register to use this field part of this R bar register. However, to let the MPU block know that we want to pick up this the MPU region number from this field, not from this register, we need to use this valid bit. Hence, we need to set this bit to 1 to say to the system the MPU region to be configured is the one specified in this field, not in this register. And if not, then you can keep this valid bit to 0, and the system will pick up the region number from this register. Finally, we have this RASR register, and this one is used to assign the different memory configuration in terms of access to our selected MPU region. Here in terms of execute, access rights, whether in terms of read or write, as well as memory attribution like bufferability and cacheability. We define as well the size of the MPU region to be protected within this field, and of course we can enable or disable separately the check against this defined MPU region via this bit. So guys, as a proof of concept, we will use an STM32 microcontroller, and we'll use a Keil-defined project to create our custom memory region and then try to access some memory address that is protected or covered by this defined MPU region. And we will see that if we forbid the access to this MPU region, then accessing a memory address that is covered by this MPU region will lead to memory managed fault. So first of all, we'll need to enable the separate trap of the memory managed fault to prove and then demonstrate that accessing a memory address that is protected by our MPU region will lead to a memory managed fault. So this is done via accessing this SCP register, as we can see here. We need to make sure, of course, that the MPU is disabled before we start reconfiguring basically the different MPU regions. Now we select the MPU region number to be configured. So we'll use basically the default setting via this RNR register. And hence, this RNR register will be acting as input to our MPU hardware mux. And based on this number, the corresponding R bar and RTOS register will be selected. Here, we are defining basically the base address of our MPU region to be protected. This is an STM32 microcontroller. So the SRAM will start from address 20 million. So I will try to protect address 20 million up to 20 million and 1 kilobyte. So the size of the MPU region to be protected is 1 kilobyte. So here I define the start address. And then in the RTOS, I need first of all to define the size to be protected. So there is already a table basically that define this size and each matching base configurations. So for example, we want to protect 1 kilobyte, which is 1024 bytes. So we need first of all to determine logarithmic base 2 of this 1024, which is 10. Then the size field will contain 10 minus 1. You can check, by the way, the description of the RTOS register to determine basically this formula. But as you can see, just we need to determine the result of the logarithmic base 2 of our size to be protected, then minus 1. And hence we'll get basically the value to be programmed into our size field. Then we need to shift it by 1, because bit number 0 is reserved to separately enable or disable our MPU region. And then this will be provided as input to our RTOS register configuration. Here, this is the separate enable or disable of our MPU region. Of course, we'll need to enable it. Then we'll configure the different memory attributes associated to our MPU region in terms of shareability, cacheability, and bufferability. And this is, of course, another subset to define sub-region within our main region. For now, there is no need actually to configure those fields, including this text one. So I will keep it as 0, as you can see. Here, this field, starting from bit number 24, will be used actually to define the access rights in terms of read, write, and read, write. The execute actually will have its own bit, which is called X bit, as you can see. Which is starting from bit number 28. Now, in terms of access rights, I will forbid the read and write access. Hence, the value should be 0. If we want to enable, for example, the separate access rights in terms of read and write, then we need to set bit number 24 and 25 actually to 1. And to be more precise, we can check the configurations of our MPU via the register description, MPU Cortex-M register. Go here. And then if you go to the raster basically description, we can see the different combination for the size associated to the size and the corresponding actually bits configuration needed for answer to protect 32 bytes or 1 kilobyte and so on. And now for access permissions, here we have the different combinations of this cacheability, bufferability, and shareability and text space and the associated attributes to each specific configuration. And of course, we have the access, let's say, permission configurations. So here, as you can see, if we set bit number 24 and 25 to 1, then we are having full access. However, if they are reset to zeros, then there is no access. And of course, the configuration will match the privilege permission associated to our ARM Cortex-M, if it is running in privileged or unprivileged mode. Now, if you go back to our code, so this is what we are trying to do. So we are disabling the read and write access to this MPU region that is starting from address 20 million. And then we are disabling as well the execute write from this memory region. So any attempt to read, write, or execute from address or space address range starting from address 20 million up to 1 kilobyte, this will lead to memory managed fault. And finally, of course, we'll need to globally enable the MPU. So this is the bit number 0 of this control register. And of course, for the rest of the address space used by our microcontroller, we need to define default mapping. And this is via this bit number 2 within our control register. It means only privileged access is allowed to the different, basically, address space outside of our protected MPU region. And then we'll try to access the address 20 million. We run, and here we go. We are here. Then if we try to access this address 20 million via store operation, this leads to memory managed fault, and this is expected.